is a strange concept, especially when we think of it in terms of size. It might seem like the size of infinity is just infinite, but are all infinitely large things really the same?
Some infinities are simply bigger than other infinities.
Interesting thought, Hazel Grace Lancaster, but how can we know this for sure? In order to compare the sizes of one infinitely large thing to another infinitely large thing, we need some way of measuring a size of infinite proportions. Thanks to a branch of mathematical logic called set theory, we have a simple tool to help us do it: cardinality. The cardinality of a set is basically a fancy name for its size, or a number of elements, except for one key difference. Determining a set's size means we would have to count up all the elements in a set. But with cardinality, we can say that two sets have the same cardinality if there is a way to pair off their elements without leaving any elements uncovered. So cardinality is a really important concept when we're dealing with something uncountable. Now back to all this infinity business. Let's get into the mind of Hazel Grace when she was preparing her eulogy for Augustus. Her first step: write a list of all the reasons she loves Augustus. Let's call this set 1. Her next step: start cranking out those eulogy drafts. She wants to test out every possible combination of the reasons on her list in set 1. This infinitely large collection of drafts will be set 2. We could also call this the power set of set 1, or a set containing every possible combination of set 1's elements. So now, we have two infinitely large things, but how do we compare these two infinities? Remember, to mathematically prove that the two sets have a different cardinality, we need to find at least one unpaired element in either of the two sets. And we can't manually check the infinitely many combinations, so how else could we find a subset that's not here? Through a simple trick called diagonalization, which will help us find this unpaired element in set 2 and mathematically prove that set 2 is bigger than set 1. Diagonalization is a matter of two simple steps. Step 1. Create a new set that contains all of the elements in the main diagonal. This might seem a bit random, but bear with me for a second. Step 2. Create the diagonal set, which is a set that's the opposite of the set that we made in step 1. If an element is in this set, then we're not going to put it in the diagonal set. If an element isn't in this set, then we are going to put it in the diagonal set. And as we go down the infinitely long diagonal, we would just continue using this logic to determine the components of the diagonal set. We've just done something huge. We've just found an element in set 2 that is specifically different from the drafts in every single row above. Don't believe me? I admire your prudence. Let's test it out. The diagonal set and the first draft aren't equal because one contains smile and the other doesn't. The second draft, it's also different because it contains sense of humor while the diagonal set doesn't. There's a beautifully elegant pattern emerging here, and it's specifically because of the way we've built this diagonal set that none of the drafts in set 2 that have already been paired will ever match perfectly with the diagonal set. We've found it. The diagonal set is the unpaired element we were looking for, which means that even though set 1 and set 2 are infinite, by the concept of cardinality, set 2 is bigger than set 1. This is the central idea behind Cantor's theorem, which showed that every set is always smaller than its power set. This one trick revolutionized what mathematicians thought they knew about infinity. Even between two sets that are infinitely large, one infinity is simply bigger than the other infinity. Touché, Hazel Grace.